And maybe also good to know, since last year she's associate editor of Dalton Transactions. So maybe if you have some general publishing questions, also something. So Maarit, thank you for joining us, and then we'll be looking forward to your lecture.
Yeah.
Maybe I should say that, well, it's quite obvious that the lecture is being filmed, so just that you know that. Yeah, ask smart questions. And this will end up on the YouTube channel of the Hybrid project as well. So if you want to rewatch it later, then we'll share it, because not everyone can be in this room, of course. Then, okay, Maarit.
Okay, so may I
just,
because it's otherwise quite difficult to speak.
Yeah.
So thank you very much. I'm happy to be here, and it's a first travel for me after 2 years, so quite exciting just to fly here and visit your group. But I'm happy that this was possible, and also I'm very happy that I was invited to give this lecture and tell you a little bit of our research. And as was already mentioned by Rob, so this presentation is on combined atomic molecular layer deposition technique for hybrid materials. So I have a few slides about the approach. As such, I guess you all know ALD technique, and probably you are not so much used to this combined ALD-MLD technique, I'm not sure, but in any case, I have a short introduction to that. And then I selected 4 application areas where we are applying this technique. So lithium-ion battery. So for that, we are making lithium-organic crystalline hybrid materials. And then we are also working on upconversion, thin films, hybrid materials, lanthanide, organic materials for possible application in PV technology. And then thermoelectrics is the third application. For that purpose, we grow metal oxide organic superlattice thin films. And then also superlattices are involved in this 4th application, which is flexible and switchable magnetic thin films. And but my background a little bit more still. So basically, I'm inorganic chemist and working for new materials. So in all of these approaches, so my main goal is to make something unique or new materials, and then the applications are secondary things. So we are not working on just a single application trying to improve and optimize the materials for that, but rather the philosophy is that once we have a new unique materials, so probably there would be chances that they would show unique properties which would be useful for different applications. And I'm not only working on thin films, and also my real background is not in thin films. For example, I was working for 10 years in Japan, and on that time I was working for bulk materials, but the new materials. So new materials is the dominator for all these studies, and typically transition metal oxide materials. I started with high TC superconductors, and this thermoelectric materials has been quite long with me for bulk materials initially, and also different perovskite related magnetic materials. I have been working for a long time for bulk applications, and also ionic conductors for different applications. And then in the laboratory where I am from, so this ALD, it's one of the early actors. So the previous professor was Lauri Niinistö, and he's one of the very early researchers in the field of ALD technology. And he was my supervisor originally, and actually I was the only student in his group who was not working on ALD. So the only one working on bulk materials, and all the rest were working on ALD since already 1980s. And only when I came back from Japan, 2006, and Lauri Niinistö retired, so then I found that there were quite many ALD reactors in the lab, so I thought that I should start to do something with those ALD reactors, and then I started my work on those. But I kind of continued my philosophy of making new materials, so and also because it was so much long background in ALD technology for known processes, so I thought that I need to use ALD for new materials. And actually, I have also, even now, so we are working on bulk materials as well. So I also have a kind of unique synthesis tool for bulk materials, and this is ultra high pressure synthesis. So we have this kind of 2 ultra high pressure machines in my laboratory, and we can reach with the smaller one up to 5 gigapascals. So this is equivalent to diamond synthesis. So we can make quite nice new perovskite materials, for example, for different magnetic applications, for instance. And this bigger one, we can even go up to 23 gigapascals. So it's a huge pressure. And then this is a little bit old photo from our ALD lab. So first of all, we don't have any nice clean room there. So and also most of the reactors are very old, F120 type reactors. So from ancient times, they were already old when I inherited those 2006. So I don't know how old they are. And a little bit old photo. So now we have 2 new picosan reactors as well here. In this photo, only 1. But still, I think, especially for these ALD-MLD applications for hybrid materials, these old reactors are the best because those can be tuned very nicely for different purposes, and we need not to somehow worry about cleaning up them. Because, and in any case, those are most flexible.
And very few cold spots. If you have very few cold spots.
Yeah. So just few words about the ALD, MLD. So assume that all of you know ALD, so atomic layer deposition for high quality inorganic thin films, where we have 2 precursors. So we have typically the metal precursor, and then we have a co-reactant. For example, if you want to make a metal oxide, so it's quite often just water. And then we pulse them in the reactor 1 at a time, so that is the difference. So maybe many of you are working on CVD techniques, so that is the difference, that we pulse them 1 at a time, and always we have this purge pulse here in between, which is typically inert gas, in our case nitrogen gas, pulse to clean the reactor space from the first precursor before we put the second precursor in the reactor. Then there is this MLD technique, and actually this was, so ALD was introduced 1970s, but this MLD is also quite long history. So the first papers are from Japan from early 1990s. So this was for purely organic thin films. And it was named molecular layer deposition because here we grow the film not atomic layer by atomic layer, but molecular layer by molecular layer. And the principle is just the same, and the difference is here that we just have 2 organic precursors which are reactive towards each other. But we are not working on this MLD, so there's also somehow naming difference. Some people use this MLD name for hybrid materials as well, but I want to distinguish our hybrid process from this MLD technique for purely organic films. So I call it ALD-MLD because we are combining metal precursor, just a similar precursor what we have in ALD, and then we just replace the, for example, water pulse in conventional ALD, we replace by 1 organic precursor, and then we can grow metal organic thin films layer by layer. So some people also you see a lot of literature calling this process MLD, but for me, I prefer this ALD, MLD. Recently, maybe other groups are also following this naming more and more. And just to show how widely used, or not so widely yet, this ALD-MLD technique for hybrid ones is. So for the pure organic ones, I mentioned that the first papers are from 1990s, but there are just very few papers. And the first scientific paper for this combined ALD-MLD technique was from 2007. Here are the first papers and the groups publishing those papers. And we started the work for ALD-MLD 2009, and our first paper is from 2011. But since that, we have done quite much in this field. And I don't have yet here shown the 2021 numbers, but they are much higher than last year. So that's a nice increase in the interest on this ALD-MLD. And what kind of processes so far developed? I always like to show this figure because this is typically shown also for the ALD processes. And for conventional ALD, the processes regarding the metal component or cation component in the film covers the whole periodic table already, almost. But for the ALD-MLD processes, we don't cover yet the whole periodic table, but already quite many. And from each group, so we have processes for alkali and alkaline earth metals, then transition metals, and then just main group elements here, and also for the lanthanides. So, and each time when I'm showing this figure in presentation, so at least there's one or two more elements covered. So we are going to fill this periodic table also for ALD-MLD. So there's no reason why the other elements wouldn't work as well. It's just a matter of doing the work. And the precursors are basically, for the metal precursors, they are essentially the same metal precursors used in conventional ALD, so we have the availability for those. But then for the organic components, so of course there we should do more consideration. And this is just, I think this is very updated version of the collection of all the organics so far used in ALD, MLD, not only by us, but others as well. And those numbers you can see under each molecule. So those are the evaporation temperatures used in actual ALD-MLD depositions. And then here, of course, the limitation for selecting the organic precursor, one of the important limitations is this evaporation temperature. So we can, of course, heat the precursors, but not higher temperature than the actual deposition temperature. And I think this is 260 is the highest we have used for heating the precursors. And then, of course, there's a problem probably that some of the organics would decompose before evaporation. But those are at least working. And of course, there would be plenty of space finding new organics as well beyond those that have been used so far. And then, of course, when selecting the organic components, so we have a little bit more consideration what we should do, and also this is, of course, our freedom, because then we can introduce many nice things in our films. So first of all, of course, we need to select the backbone of the organics, and this is, of course, the part of the organics which is remaining in the film. So also, of course, how long this is, that's one parameter, but also we would like to also include some additional functionalities if possible, and if designed so. Then, of course, we need the functional groups, because those are needed for the reaction between the or with the metal precursor. So those should fit the metal precursor. And there's a kind of analogy. So in conventional ALD for metal organics, so water is a common second precursor. And if we want then oxygen bonding to the metal between the organics and inorganics, so quite often we use diols or OH groups as the functional groups reacting with the metal precursor for the organics. Then we can also use amine groups, and this is a kind of analogy to the nitride films in ALD. And then some ALD metal precursors, they require more strongly oxidizing second precursors. Typically ozone is used in ALD, and carboxylic acid groups are kind of equivalent. They typically react in the same way as ozone reacts in ALD for those less reactive metal precursors. Then for the backbone, so I said that of course not only the size, that's of course important factor, but it would be nice to introduce some additional functionalities. And these are two quite recent examples from my group, what we have been somehow thinking and also using and showing that it works. So we thought that it would be nice to make antiviral coatings, and curcumin is known as an antiviral molecule even against COVID, and we could use this as a precursor for our hybrid films. Required quite high evaporation temperature, but it still worked, and it seemed not to decompose during the deposition. And another nice molecule is this azobenzene moiety here, because it's known to be photoresponsive. So once we illuminate it by UV light, this transform, which is more stable under normal condition, it transforms into this cis form, and there is a quite big size difference. So if we can introduce this in our films, so then of course once we UV illuminate the film, so we can squeeze the dimensions in the films. And this also worked quite nicely. I'm going to show examples on that azobenzene molecule. Then there's of course has been and was already for a long time kind of dream to make these metal organic films made by ALD/MLD to make them crystalline. But people were quite pessimistic if it were really possible, because even many ALD films, they don't come as crystalline. For example, aluminum oxide, it's always amorphous, and hafnium dioxide used in transistor technology, it's amorphous when deposited by ALD, and actually it's really needed to be amorphous, so that's the target. But of course some of the films easily come crystalline, like zinc oxide. So it was a question that is it possible to make ALD/MLD hybrid films crystalline. And the first in situ crystalline films were these copper terephthalate films. We reported this 2016. And the diffraction pattern was quite close to the known MOF2 crystal structure. Then of course the question was that what is exactly the crystal structure? Is it this one or modified, and also if it's porous or not? And this is the topic we are now collaborating to really show it, if it's a porous MOF structure or something close. But there are many other, after this first success in making in situ crystalline films, so I think roughly 20 processes have been developed which show in situ crystalline films here, I have just 2 other examples. Quite many are based on alkali metals, and our somehow idea was that if we have a more ionic bonding between the metal and the organics, then there's a more freedom for the arrangement if we don't have a somehow ordered covalent bond. So probably during the film growth, this kind of ionic bonds are making more easily crystalline films, and at least it seems to work because many of those are based on alkali metals, but not all. But this is one example and quite interesting one. So based on lithium and then benzoquinone as the organic component. And this is an example of a case where there were no bulk equivalent. So this compound has not been made by any solution technique for bulk material, so we didn't, of course, know the structure. But there is a sodium equivalent, so we predicted the lithium-based structure by DFT, and then, of course, confirmed that the diffraction pattern and IR pattern corresponded to this predicted structure. And here, the lithium is very much under-coordinated, so coordination number is 3, and this means that it very easily takes the solvent molecules attached to it. So that's probably the reason why it cannot be made from solution, but it's easy to make it directly from gas phase. And this is also nice because this turned out to be very good cathode material for lithium organic battery. And then here's a third example of in situ crystalline films, and this involves now this azobenzene, this UV active azobenzene molecule, and this is iron is the metal component, so it's not necessarily need to be alkali metal, but can be also some other metals for crystalline films. And this we also could demonstrate. This is also a new material. There is no bulk equivalent for this. Nobody made. Possibly this could be made, but just not made so far in bulk form. So we don't know the structure. We have some idea for that, but no clear crystal structure known. But what we could demonstrate is that this is UV active. So we can transform this trans form of azobenzene into cis form if we UV irradiate our films, and it's also reversible. And it's quite nice because also we could see that this easily absorbs water molecules, but when we UV irradiate and make this organic smaller, so water comes out. So there's a kind of some switching effect. And it's also reversible, so it's quite difficult to. So there are works where people are trying to put azobenzene in some MOF materials, but it's difficult to realize this trans-cis isomerization reaction, because then typically the structure is broken. But probably in our polycrystalline thin films, there is more freedom to achieve this transformation and reversibility for that. So that's a good thing for polycrystalline thin films. Now I come to my application examples, and starting from the lithium-ion microbattery. So I already mentioned that this lithium benzoquinone crystalline films. So this material turned out to be, and we could also predict that it could be good cathode material, and it really turned out to be so. And also we were able to make lithium terephthalate thin films. They are also in situ crystalline, and this compound is existing in bulk form, and this is one of the compounds highlighted already a long time ago by battery people working for organic batteries, so as a possible anode material. But it doesn't work very well in bulk wet cell batteries because this is very reacting with the water, and also the electrical conductivity is not very high for any of those lithium organic materials. But if we have a thin film construction, so then this lower electrical conductivity is not so bad problem anymore because the conduction paths are so short. Then we also had developed purely inorganic process, ALD process, for the state-of-the-art electrolyte candidate for the thin film microbattery, so-called LiPon compound, so lithium phosphorus oxynitrogen compound, and we could combine those three processes to make fully ALD-MLD made lithium ion micro battery. So the individual layer thicknesses vary between 10 nanometers to I think 40 nanometers. So I don't recall exactly. And basically the whole thing can be done in one shot in ALD reactor. And it also was shown to be fully functional, so electrochemically active. So of course it's far from optimized for the battery application, but we could recycle it, I mean load and charge and discharge the battery maybe 10 times or something like that. So it works, and the charging, so basically the power density is very high, and it's very fast to charge, so just less than 1 second and we can charge the battery. But of course the clear drawback is the very low energy density because the films are very thin. So of course the solution is known what we should do, and that is to make it 3D. I think IMEC is one of the leaders in this, designing those 3D structures, and then develop all those processes so that we could deposit the configuration, this 3D configuration, and thereby enhance the energy density. So it should work, and of course ALD-MLD should be fully conformal, but in practice of course this requires a lot of effort to really optimize these batteries. But I think in principle it's a somehow good idea, and probably our capability is not anymore to really optimize the battery. So, but what we have done is to also develop new possible electrode materials to replace those lithium terephthalate and lithium kinon anode and cathode materials, and we have already demonstrated quite many new ALD-MLD processes for these materials. So for example, we can increase or play with the backbone of the organic molecule. So those 5 we have demonstrated, and also we can add additional functional group, like an amino group here attached to this benzene ring, which is known to be electron donating group. So this decreases the redox potential. So this could be better candidate to replace this terephthalate compound as the anode, because the redox potential is a little bit high for this terephthalate acid, but it's a lower for this amino functionalized material. So there's a lot of course, more possibilities to fine-tune these materials already partly shown here. And all those are crystalline, in situ crystalline films, and not all were known. So this azobenzene lithium compound was not known from the structure, but it's a crystalline, and those others were known the crystal structures from literature, and our diffraction patterns correspond to those. They are not porous, but they are two-dimensional structures, and actually they have been highlighted so-called intercalation type of structures. And the good thing here is that when lithium is intercalating to these structures, so there is not much of volume expansion, so that's very good for the battery performance. So basically those are quite nice material candidates, all of them. Okay, then there's also another maybe more relevant in near future application possibility in lithium-ion battery technology for these hybrid films made by ALD/MLD, and this is in so-called artificial SEI barrier layers. So I'm sure you know the function of a conventional lithium-ion battery, and especially the importance of this solid electrolyte interface, which is forming naturally. We cannot avoid it, so this is due to the fact that the liquid electrolyte reacts with the anode material. With all the known liquid electrolytes and anode materials, we get this reaction layer here. So this is, of course, we don't want to get it, but at the same time it protects from the further reaction, so that people can use the ordinary conventional lithium-ion batteries. But of course, there's always the question that, first of all, when this is formed, when we start to use the battery newly, so it consumes part of the lithium from active lithium, which should be used for the battery action. So that's one drawback. Another thing is that if this doesn't form, if there are some imperfections in this SEI layer, so then there may be some explosion then. So the idea is to make artificially these SEI layers before we start to use the battery, so that the anode material would be coated by this artificial SEI layer. And then, of course, ALD would be very perfect, and there's a lot of research going on by coating anodes by ALD for inorganic films. But actually, if you look at the composition of this natural SEI layer, so it is not inorganic, but it's hybrid composition. So it's basically lithium ethylene carbonate, the composition mostly for that film. And so the idea is that of course it would be good to mimic that real composition and then develop ALD/MLD process for that. And this is what we have done. So it's this kind of three precursor process. So we have the lithium precursor, and then this ethylene glycol for the organic component, and then we also introduce carbon dioxide as the third precursor in this process. And we have made those films, so it's very well-behaving process, but we haven't yet demonstrated how useful it could be in real lithium-ion battery application. That, of course, requires a lot of work and also probably collaboration with the best battery researchers. Okay, that was about the lithium-ion battery applications for these hybrid materials. I wonder if I haven't used too much time. No. Okay, I'll go fast at these other examples. So this is the second possible application, and this is for luminescent materials, and especially we are working on upconversion materials. So the upconversion process is known for some of the lanthanides, typically erbium, ytterbium, and holmium ions. And it's an accumulation of excitation energy, so that typically the excitation would be in IR range, and for example, erbium can accumulate to photons, and then we get the luminescence when those excited electrons return back to the zero state. And typically then this emission is in visible light, so that we can convert IR radiation into visible light. And that would be, of course, very nice, for example, in solar cells, because solar cells are utilizing only the visible part of the solar spectrum. So if you could utilize also part of the IR, that would be enhancing the efficiency, conversion efficiency of the solar cells. So that kind of materials have been considered, and it is known that the lanthanides are the good active for this emission process. But the problem with the lanthanides in inorganic matrix is that their absorption for IR radiation is very weak. So we need some sensitizers. And organics are known in principle to absorb very well IR radiation. So there has been idea to combine those, so organics with the lanthanides. And there has been research going on ordinary metal organic complexes, so just molecular materials. But there has been a problem because there is very strong ligand vibrations in those complexes, and that end up with the energy losses, non-radiative energy losses. So the ligands absorb, but then they also lose the absorbed energy. So our very simple-minded idea was, or somehow we thought that might be possible if we do these metal organics, so that in the films the organics are more strongly bound. So probably those vibrations are not so strong for the organics as they are in metal complexes. So probably we could minimize these energy losses, and it seemed to work. So this is our first success. So the metal composition is a mixture of yttrium, ytterbium, and erbium, and pyrazine is the organic component here. And we could get very nice visible light with the IR radiation, and even within the whole visible range, so blue, green, and red light out of this. And now we are working on combining this with the solar cell technology, and we have used those silicon solar cells. And so far we haven't really made this ALD-MLD coatings, but we started with just the ALD coating on silicon solar cell, and we used erbium holmium oxide ALD coating, and this worked so that we could improve the performance of the solar cell by 3%. And now the next step is to work on these hybrid materials. So this is just very much ongoing. So these are only the first results for this application. Okay, then my last two applications not for this kind of one-to-one hybrid materials, which can be, as I said, they can be amorphous or crystalline. And actually those lanthanoid-based upconversion materials, they were amorphous, so there's no need to be crystalline for that application. But with the ALD-MLD, very nice thing is that once we have this kind of well-behaving process for one-to-one hybrid, so it's very easy to play with the sequence of ALD and MLD precursor cycles. So we can, for example, make a thicker inorganic layers and then just a single organic layers in between, and make this kind of super lattice materials. And this is actually very good for many applications. So we can have a metal organic layers, let's say 10 nanometer thick, and then just a few organic layers there. And of course, A nice thing is also that we need not to place those organic layers in a regular fashion in the film, but we can put them in any frequency, so make also this kind of gradient hybrid materials. So there's a lot of freedom with the ALD MLD to design and realize this kind of multi-layer structures. And we have been especially much playing with the zinc oxide, because zinc oxide is a interesting semiconductor for many applications, and also the ALD process is so well known and easy to handle. And this is just how we confirm those super lattice structures. So of course this is our imagination when we are designing these films. So we are designing that we have the zinc oxide structure, and then the organic layers bonded in this way. And then of course we check by GI-XRD that the zinc oxide structure remains there. I don't have the evidence here, but it's very much well preserved. And then we use X-ray reflectivity as the first tool to see that we have this regular superlattice structure. So we see this kind of stronger superlattice peaks there. And just by counting how many smaller peaks here, we know what is the superlattice period. So it's easy to confirm that the layer sequence is exactly what we want. So that's very straightforward. Then, of course, for some of them we have this is not easily achieved in my group, so we don't have a high resolution TM, but in some cases we have demonstrated that we can really see those single organic layers there as well. Then there is, of course, a question how those benzene rings are bonded in this case, and it's very difficult to really investigate this bonding structure, but we have done DFT modeling for that, and this is the result for this zinc oxide benzene case. So actually the benzene ring is bonded not to each oxygen atom here or zinc atom, but just every second, so in this way. But how these are useful, so especially very useful for thermoelectric application, and this is something we have been working quite long already. So these are a little bit older results partly, but why these superlattices are so good for thermoelectric? So I guess not all of you are very familiar on thermoelectrics, but in short, thermoelectric material can convert waste heat directly into electricity, so it's a very attractive possibility, but the conversion efficiencies for known materials have not been as high as we would like them to be. For example, not as high. Solar cells are much better converters, energy converters, than thermoelectrics. And the difficulty is that we don't have perfect materials for that purpose, because the material needs to be at the same time very good electrical conductor, but thermal conductivity should be as low as possible. So that rules out the metals, so they are of course good electrical conductors, but also very good thermal conductors. So certain semiconductors are somehow kind of compromised, and zinc oxide is relatively fine among the simple materials, but still the electrical conductivity is fine, but the thermal conductivity is too high. So we should be able to lower the thermal conductivity without decreasing the electrical conductivity. And this can be very nicely achieved with these superlattices. So if we just introduce monomolecular organic layers within the zinc oxide thin film, typically this thickness could be something like 5 or 10 nanometers each individual zinc oxide layer. So they are electrically conducting as not much difference even though we put the organics there compared to the pure zinc oxide films. But the thermal conductivity, so phonon conduction, is trapped very effectively at those inorganic-organic interfaces. And by introducing just a few organic layers within, typically our films are something like 100 nanometers, so we can reduce the thermal conductivity by factor of 50. So it means that we can make the material 50 times more efficient for this thermoelectric conversion by these organic layers. So it's really a nice concept for producing the thermal conductivity without affecting the electrical conductivity. Then there are other nice things with this ALD technique, because such thermoelectric materials, they are investigated for wearable applications, so that we could convert body heat into electricity and power all kind of wearable gadgets. And there's a lot of research going on in that field. And so it would be nice to integrate these films with a textile. And ALD-MLD is very nice for that, because first of all, those are mechanically much more flexible than pure inorganic films. So we have shown it for many of these hybrid thin films and super lattices, not exactly for this zinc oxide, but there's no reason why they wouldn't be as well. But also if we deposit these on textile substrate, so this is just ordinary cotton textile, so ALD films are grown all over the textile fibers, so that this textile also becomes part of the device. And this is very good for thermoelectrics, because in this field, the thicker the better, so the thinnest films are not the best. And so ALD is not perfect in that way, because it's relatively slow. But once we can, in one deposition, we can grow all over the textile, so then we get much thicker films, and that should be useful. So this, I believe, is quite nice for possible applications. The problem is that we also need P-type materials. So for thermoelectric device, we need to do this also for P-type materials, so zinc oxide is N-type. And I think those organic materials investigated here in this university, they are P-type, so it could be combined with this. Okay, and just one more small feature. I mentioned that with ALD-MLD, we can place the organic layers wherever we want, so not only in a regular fashion, but in this kind of gradient films we can do. So we can do the same thermoelectric zinc oxide-based films also, so that we put the organic layers in this kind of disordered fashion. And actually, for blocking thermal conductivity, it's known that the disordered systems are typically more efficient for lowering the thermal conductivity. And it is also seen here, so that the thermal conductivity is lower if we keep the same film thickness, same amount of organic layers, but put them in a random fashion, so thermal conductivity is lower. Okay, still some time for my last example, and this is on magnetic thin films. And there is a need for room temperature ferro or ferrimagnetic films, which would be also flexible. That would be nice. So basically, if you could make ALD-MLD magnetic films, so there might be very good application possibilities for that. But of course, there are not so many simple materials which can be made by ALD, which are room temperature ferrimagnets or ferromagnets. But there's one very exciting material. It's an epsilon modification of iron oxide. So this is not hematite, which is antiferromagnetic, but this has a different crystal structure. And this has been known since 1934. First observations are from that year, and it was synthesized. The difficulty is that it's very unstable. So it could be synthesized in very small quantities only, in kind of bulk form, so in nanocrystals, and the applications, of course, were not possible for that small amounts. But the magnetic properties are really exciting. So it's a ferrimagnetic, and the Curie temperature is nearly 500 Kelvin, so it's pretty high. And what is especially attractive is that it has a very high coercivity field. So it's a very hard magnet. And that's really important for some of the applications. So there were some success in PLD processes 10 years ago, but we were lucky and developed ALD process for these epsilon iron oxide films 2017. And this is quite amazing because very simple precursors, so iron chloride and water, and it just yields this epsilon phase in situ crystalline films. And also we could demonstrate for these films the ferrimagnetic properties at room temperature, and also this very high coercivity field. So it's the width of this hysteresis curve is the coercivity field. So these films showed really exciting magnetic properties, and also they were very stable. So we could even anneal these to enhance the crystallinity, although it was not needed because they were even in situ quite fine. And of course, ALD is still kind of possible for mass production because it's able to coat large area surfaces. So this is very good progress for utilizing this exciting magnetic material. And even more because these were so stable, these films, that we could introduce even these organic layers in between into these superlattice structures in the same way as we have been doing for zinc oxide. So we can see very nice superlattice structures from XRR patterns, and also those organic layers didn't destroy the crystallinity and this epsilon iron oxide structure of the films. So we could put here's a 0, 8, 10, 20 organic layers, and the crystallinity just remains the same. And also the magnetic properties remain the same. So especially for this coercivity field. So this width is here exactly the same. Of course, if we put the organic layers, replace some of the magnetic iron atoms, so the absolute magnetization decreases, but that is not the problem, because the interesting thing is this width of this hysteresis loop. And at the same time, mechanical property testing showed that these are really very flexible, so the tensile testing showed that that is improved by many factors. And the very final achievement, we just published this 1 week ago, is that we were able to introduce photoswitching effect in these films. So we used this azobenzene. I already described this behavior, transist isomerization in the films, and it means that if we have in this superlattice, we have these magnetic epsilon iron oxide layers, and then we have this monomolecular azobenzene organic layer. So when we irradiate it by UV light, so this transforms into cis form, so it's squeezing this organic layer and bringing those magnetic layers closer to each other. And what we could see that, and this was also reversible, so when we irradiate it by visible light, so we can get it back to the transform, and this affected the magnetic properties as well. So these are the coercivity field values before UV light, then it increases, and also this is the magnetization value. So that increases, and then visible light radiation brings it back to the original values. So we have a switching effect for the magnetic properties. So we cannot yet cut the magnetic properties to 0 or somehow between 0 and some value, but this is a clear effect, something like in a maximum, not for this experiment, but in maximum it was a 20% effect, but it was reversible and clear. So we expect some nice applications for these films as well, but this is really recent discovery. Okay, so now I came to my end. I'm sorry if I used too much time, but I just wanted to show that by ALD-MLD we can make really new types of materials. That is, of course, my major interest as an inorganic chemist. So we can make all kinds of new types of hybrid materials, new MOF-like materials, and also layer-engineered super lattices in a very nice way. And many of these materials are totally new, so they probably cannot be made by any other technique. So in that sense, it's unique, and already quite many novel properties and application possibilities have been discovered, but I'm sure there is quite a lot more to be discovered for these materials. So I thank you for your attention, and I just show the name list here for those major papers which I discussed here, and so you can see the names of the students and postdocs. Those are marked in red, and then by blue our major international collaborators in blue. So, right. Thank you.
Thanks for the overview. I'm sure there are questions. Are there questions or talks?
Hi, Prof. Karppinen. So my question is more like general and the nomenclature on the use of MLD and the term crystallinity when we attach it to the material. So really two things. The first question will be, how do you make sure that when we say in the community molecular layer deposition, are we that strict that it has to be like monolayer, like bi-monolayer as with ALD, the traditional inorganic oxides and the nitrides? And then the crystallinity is, it's a little bit tricky, as you would know, for the hybrid materials, that it's not really all the time purely crystalline. It can be a mixture of amorphous and crystalline layer, but of course it would diffract if there's sufficient crystalline material. So, as an expert and as an editor of the journal, how does the community feel about this use of terms in manuscripts and in publications?
So you have had many questions in a sense in a one, but so one was that is it really monolayer by monolayer growth? Of course, that's also typically not the case in ALD either. So typically we get less than one monolayer in ALD, and the first most conventional explanation is that if there is a steric hindrance due to the big precursor molecules, so of course they cover part of the surface, so that we get the fractional numbers, not one monolayer but less than one monolayer. And of course the same applies also sometimes in ALD-MLD as well, but quite often we rather get higher growth rates with ALD-MLD, so that we are, in some cases we are very nicely just exactly getting the growth rate is the same what we expect if we know the size of the organic molecule and the metal and what we could predict for that. So I have many cases where we exactly get or very close to that expected growth rate, and that's of course due to the fact that in those cases the precursor molecules have not been consisting of very big ligands for the inorganic. So in that case we get typically for iron chloride or titanium chloride as the inorganic precursor. So that monolayer growth, in that sense, it's very similar to ALD. So sometimes we get less than monolayer, and there are good reasons for that. Then, of course, if we have organic layers there, so people are thinking that it's a kind of porous matrix, so it is possible that inorganic precursors, when we apply them, so they may diffuse within just under the surface, and we get the kind of precursor reservoir in the films. So that may happen in some cases, and this was typically for those early experiments. That's why people have so strong notion on that. And in those, typically ethylene glycol was used, and those aliphatic, non-aromatic molecules. So typically those were more, randomly oriented, that there were more space in those organic layers, and also those smaller organic layers could diffuse within the growing film. So we are mostly working on these aromatic, a little bit bigger ones, and also if the films are crystalline, so I think in situ crystalline, so it prevents this kind of diffusion. But even in those cases, the films, the processes are very well controlled. So I don't think that it's very harmful. Nothing is perfect or ideal in any case, but I think many of the processes are very close to the ideal, what we expect. But of course not all, so we should be critical. And also mention, and sometimes it's not harmful at all. So sometimes it's even used for so-called enhanced growth, so that we can grow faster if we can accumulate the excess precursors somewhere in the films, and then we get the goal. So it's possible to be quite close to the ideal, but of course not always, and of course we should be able to discuss it. Then for the crystallinity and amorphosity, so of course it's very difficult to rule out the small inclusions of amorphous parts, but I think for many of those crystalline ones, I don't believe that, of course we don't see typically in diffraction pattern that kind of amorphous contribution. Of course there may be some, and especially initially probably. So that applies to inorganic films as well. So we don't know if it's the very first layers are crystalline and so on. But I don't see any difference, with other systems, so in that sense.
So it's not like it will be rejected or something?
No.
Thank you.
Max, you have a question?
Yes, thanks for the interesting talk. I have two questions. One application very well maybe, so for these micro batteries, the lithium precursors, are they expensive?
We have used two types of lithium precursors. I haven't really paid too much attention, so it means on the precursor prices. So I think they are just ordinary precursor prices, so we haven't used anything special.
So not
Yeah. No, yeah. I would have noticed if a student would order something very, yeah.
Photophysics, so on the up-conversion device, so it's not so efficient, it looks like. Is it because the quantum yield of the up-conversion is low, or is the absorption, so I suppose you coat the film directly of the silicon solar cell.
Yeah.
Does it take visible light also away, or does it mostly absorb in the infrared and then?
So the work, we only have one demonstration for real silicon solar cell, device coating, and we used artificial sun. So it was not a laser. In those first ones, when we investigated just the up-converting films as such, so we used laser excitation, so just one single line. But for those with the silicon solar cell, we used artificial sun, and I think the intensity is 9 times the real sun. Yes, yeah. But I'm not really, solar cell person. So, but luckily we have a really good expert at Aalto University, Hele Savin, who is working on this silicon solar cells.
So you don't know exactly the quantum yield of the up-conversion?
No, not separately, no. Okay. What we just then could measure is the light conversion efficiency of uncoated and coated. Yes. And we coated with different thicknesses, so we could see that that I think we had three different thicknesses, 40 nanometers, 50 nanometers, and 70 or something like that, I forgot. So with the increasing thickness, so this enhancement was increasing a little bit, but all were increased compared to the uncoated. So it was promising result, but totally not optimized at all for any parameters, but just the concept works. But it was considered quite good improvement, 3%, because solar cell, at least to my knowledge, it's kind of they already reached the with all the possible tricks the highest conversion efficiency. So there is no other way to enhance anymore. So yeah.
And what is the thickness of the films you deposit?
I think the thinnest were 40 nanometers and thickest one maybe 70 nanometers. So
40 to 70.
yeah. We just selected those because typical ALD thin film thicknesses, and yeah. So we didn't go into thicker ones yet, but now the project is going on. So, and we are also considering other solar cells as well. Actually, it could be more efficient or more useful because silicon solar cells are rather utilizing the IR part more efficiently compared to the other solar cells. So this is the the part utilized by the solar cell itself. So, for example, these ytterbium and erbium ones are used in some studies for other solar cell types, but they are not useful in the case of silicon, because in any case silicon itself is absorbing part of the IR in that range. So what we used was holmium here, so because it has as the most active component there, not ytterbium. But those could be used, they are probably more efficient for other types, so those should be also optimized depending on the solar cell type.
So you actually coat the layer not on the cell, you coat it behind.
Sorry?
You coat the layer not on the cell, you coat it behind the cell.
Yeah. This was the choice of those solar cell experts. So. Yeah.
I was wondering, for the thermoelectrics, when you have these coatings that are 100 nanometers or less, how do you measure the thermal conductivity through the coating like that?
Yes, it's a it's a cross plane. Yes. So we do it. We have a best experts in US who are using so-called DDTR technique for that. Yeah, and it's only cross plane measurement, and of course what we are measuring for electrical conductivity is in plane measurement. So that's why I typically don't want to combine those for the performance or figure of merit number, because we are measuring. But those are polycrystalline films, so it should not be somehow so. It's a standard, way for all the thin film, thermoelectric thin films, how people are doing, because in plane thermal conductivity measurement, it's difficult for thin films.
Yeah, because you have your substrate.
Yeah.
And how does a true plane work exactly? So you heat it from outside, and I guess you.
I haven't done it by myself, but yes.
Yeah. I was wondering.
It needs to be glass substrate, so not silicon, but yeah.
Since you measured ozone as well in one of the slides as a comparison with the inorganics, did you ever try to use ozone to oxidize the organic components partially on the surface? It's a bit of concept that Dimas, where you take a more volatile precursor and it reacts on the surface.
Yeah.
I guess there is a scenario where you could use an alcohol and oxidize it to a carboxylic acid.
Yes. So we haven't worked on that, but we have been thinking it as a possibility. Yes.
It should be possible.
Yes.
Other questions at the moment?
Maybe I can ask a short question about. You had a slide about precursor temperatures used in different MLDs. Is there a particular vapor pressure that you're usually aiming at? Is there like a number that you want, I don't know, 1,000 pascals?
So not in that way. So we haven't measured really those vapor pressures, but of course in our reactor we have the pressure is 3 millibars typically, roughly, and those numbers what I showed, they are practical, not only our own ones, but of course many of those are from our own work. But they are what have been used in practice, just from reported papers. So what people, and in our case, we always just optimize it in practice. So we first get some ideas. Sometimes we have a TG measurement. We can do it in vacuum once the thermobalance works, not always. So sometimes we have a pre-notion from the TG measurement if it's not in vacuum, so we have a notion how much the vacuum would roughly affect it. And if we don't have that, even so, then we are just looking at the melting points and we get a rough idea. Then we know the area, and then we just optimize it in practical depositions. The heating temperature needed.
I have also a question about this thermal conductivity. So you nicely showed that it matters how you distribute the interface.
Yes.
And do you know what's the mechanism of this? And is this experimental results or is it theoretical?
It's experimental, but in general for thermal conductivity, so all the defects and impurities and symmetry lowerings are known to reduce the thermal conductivity, just any material. So the best thermal conductor is a diamond, so it's a symmetric, very light elements, and everywhere the bonds are similar and strong bonding. So if we can get as far from diamond as possible, so all those are somehow known. Of course, there are some theoreticians, but not this. I mean, predicting, but they cannot predict for all the systems. So, yeah. So we haven't really. We have predicted this for the super lattices, or collaborated with the computational chemist. So, but not really that those gradient ones would be better. So it was just somehow very simple-minded notion, because we know that the less symmetry, the lower the thermal conductivity. So, and just then showed it experimentally. Sometimes it's faster to show it experimentally than first predict. Of course, then it would be nice if somebody would explain it.
The volume fraction of the effect is the same for all different gradient configurations?
Yeah, we fixed the total film thickness and the number of organic layers for those. Yeah. And we have done quite much statistic for this very specific system. I think we have altogether 100 different compositions. So and then we have used very simple that kind of statistical analysis to look at the factors. So we have a thickness of individual layers and the degree of gradient and that kind of things, and then just also showed by this kind of simple analysis with the 100 different compositions that those our conclusions at least obey or were seen from this kind of simple statistical analysis.
I guess that the less symmetrical, the harder it is for these phonons to
Yeah. Yeah, that was kind of simple. Yeah. Of course, I'm not phonon physicist either, so yeah. That's my level of explanation.
All right. Any other questions? So Maarit will be here the rest of the day, and mostly at Dimo's events, so you can still think of some questions. And yeah, let's thank Maarit again.
Thank you.